In the last video, we saw how to compute the sample size needed in order to estimate a population proportion, either with prior estimate or without a prior estimate, in order to get the error, there it is, error, and the confidence that we're interested in. Precision is another word for error, right? How accurate do we want our interval to be, and how confident do we want to be? Now we want to do the same thing, but for means instead of proportions. And that has this formula. So this is the sample size required to obtain a oops, there I did it again. It's the 1 minus alpha times 100% confidence interval for mu with a margin of error E. There, I managed to squeeze the percent symbol in there. Okay, so, and just like before, it needs to be rounded up. And also just like before, you don't have to memorize any of this because it's all right here. Now keep in mind, because this is for a mean, the error does not have to be a decimal. Up here, for proportions, it has to be a decimal because you're talking about proportions. The largest a proportion could ever be is 1. So everything has to be decimals. Whereas with sample means, it could be a decimal, but most of the time it's not a decimal. It's something larger than that. Okay, so we are interested in estimating the mean annual income of Native Americans of the Onondaga Nation who live in Onondaga County, New York. We know from a previous sample that the standard deviation is about 20,000. So we have some estimate of S. That's not a prior estimate to N, right, or to the sample size or anything. It's a prior estimate of what standard deviation is, so it's going to give us a clue of what our S is. And again, they want us to show the formula substitution and all that stuff. So let's go figure that out. Okay, so first let's figure out the error. They say the words within 1,000 right there. That's our error. Error is your within. So you want to look for that word. That'll give you your error, which is 1,000. And there's no need to round or to make a decimal out of it. This isn't a decimal because the decimal thing is only for the proportion ones. Now our confidence level is 98%. It says it right here. Right? That means that since confidence level is 98, that means alpha is 0.02 because they're complements of each other. All right, 0.02 divided by 2 would make 0.01. So there we have that. So we need 0.01 as our alpha over 2. So now to find the z-score, in order to be able to substitute into this formula, I need inverse norm 0.01, comma 0, comma 1. Which I happen to know is 2.326, but that's okay, I'll find it. So I go to second distributions, number 3, 0.01, 1, sorry, then 0 and 1, paste, enter. And there you have it, 2.326. Technically, it's the negative one that I found, but again, it doesn't really matter because you're putting it into a formula that's going to square it anyway. Now, if you want to find it with the table, which is kind of quicker actually than what I just did with the calculator, you want to use the t-table. And remember the area in the tail we just said was 0.01 right here. So you're going to go to the very bottom of that column, and it's right there. The z-score is 2.326. That's the one that associates with 0.01. Okay, so we know that this is 0.01. For the area in the tail, we got 2.326 for our z-score. And then we don't have a p-hat. This is not a proportion problem. But we do know that S is about 20,000 according to that prior study that we had. Right there. It says the standard deviation is about 20,000 right here. So let me highlight that in pink. Okay, so that's where that is coming from. We don't need to worry about the prior thing. Okay, so how does this work? Well, n is going to be equal to, and we know that S is 20,000 times z, which we just figured out was 2.326, over the error, which is 1,000. So we need to find that value and square it. Okay, so I'm going to take my calculator and do it all at once. 20,000 times 2.326 divide by 1,000, close my parentheses, and square it. Enter. And there I get it, 2164.11. And just like before, I'm going to need to round up, right? I'm going to need to round up. So I need to make it 2165. I know it seems weird because you're not doing regular rounding, but the problem is that if you cut off the 1, if you go with 2164, you won't have the 1,000 error that you want. You'll have 1,002, say, and that's not what you're looking for. You can't get the precision, remember precision, your margin of error, you can't get the precision you want if you round down. So you must round up on all these problems. And I put that right in the formula sheet for you. Just a little reminder, it says in here all over the place, round up for sample size. See these sample size? Round up, right there and right there. Now keep in mind, I don't always ask, I might not say, what is the sample size? I might say, how large a sample? How many people? How many whatever do we need to pull? If you're asking how many you need to pull, that's a sample size question.